Welcome to the lesson number 7 in airflow and ductwork. Now, as I've mentioned in prior lessons, if you have not covered or watched units 1 through 6, please do so before you jump into 7. These lessons all build upon themselves and it does make a difference. And also, this material is adapted from Airflow and Ductworks by Leo A. Meyer from Lama Books, www.lamabooks.com. I do recommend that if you are wanting to know more about this than I cover here in this lesson, please pick up his book. It's definitely worth it. So in this lesson, what we're going to be discussing is calculating pressure losses in ductwork. Why do you need to know this? Because if you go to a house as a technician or an installer, or even as a service manager, you need to understand what is happening and you need to be able to calculate the friction loss to understand what is going on in a house. Now, the average technician walks into a house and says, yeah, it's not heating, cooling properly, or it's not happening, but they don't necessarily understand the airflow. We need to understand this friction loss to take the building as a whole and look at it, and not just the picture. The best technicians understand friction loss and dynamic loss in ductwork, and it makes a difference with airflow, and in turn, customer comfort. Okay, so let's take a look here. We have a full system here. Okay, we have filters, we have outside air intake, we have coils. Okay, by the way, that could be return air intake as well. We have a fan. We have 3 different takeoff runs. We have, let's see, what do we have on between points? The takeoff between point B and C. I have 4 diffusers. C and D, I have 3 diffusers. And then E, which is the final run, I have an additional 4 diffusers. Okay, so what we have here is we have 11 diffusers, a fan, a couple coils. One's a heating coil, one's a cooling coil. We have filters. Every one of these is going to cause a pressure difference to occur in the ductwork someplace along the way. Okay. Total pressure loss is friction and dynamic pressure loss for the outside air intake, the duct run from the O to A intake to outlet G, the filters, the coils, the fan system effect, the transitions B, C, and D, the takeoff F, and the outlet G. Every one of those is going to cause dynamic loss or friction loss. Okay, let's start with the fan effect because that's a new term we haven't talked about yet. Okay. The catalog rating of a fan is based on standard test conditions in a laboratory. When a fan is connected to a duct system, the shape of the fan inlet and outlet duct connections create dynamic losses that can change the fan's performance. That is fan system effect. Okay, you can measure a fan's performance after it is connected to the duct system and compare it to the fan catalog to determine the system effect. Okay, because a fan might act one way in the laboratory and change in real life conditions. Most of the pressure loss in a straight duct system is called friction loss. Friction loss for straight duct equals inches of water gauge or water column per 100 feet times the total duct length divided by 100. Okay, the length of straight duct system is determined by measuring from the fitting to the center line as shown in the slide. Okay, so again, we have a 90-degree elbow and coming off there we have a run to the right. The length is from the center line of the elbow to the end of the duct. Down from CL, again, CL is center line. Okay, the length is from the center line to the end of the ducts. So if I have a loss of 0.05 inch water gauge or water column per 100 foot, this duct run is 123 feet plus 18 feet plus 125 feet for a total run of 266 feet. Okay, so I have my friction loss, water gauge per 100 foot, times the length of duct divided by 100. So let's fill in our numbers. Friction loss in this case is 0.015, okay, because I'm closest to 300 feet, okay. That's where my 0.015 comes from because I said it was 0.05 per 100, okay. So length of duct divided by 100 is 2.66. So take my 0.015 times 2.66, and my friction loss for this duct system is 0.04 inches of water gauge. Okay, sort of makes sense. We never round down on friction loss, always round up. Now, most of the pressure loss in fittings comes from the dynamic loss. Okay, this handout I have a handout online at training.christophermolnar.com that will actually show you what the dynamic losses is. Okay, but for now, let's look at this table. Okay, we have loss coefficients for single thickness turning vanes. We have dimensions in inches, okay, and we have velocity of feet per minute. Okay, you'll notice as the velocity goes up, my loss coefficient goes down. Okay, the throat radius of the turning vane is R. The spacing between the vanes is S. The velocity is in feet per minute. Okay, each number under the various velocities is a coefficient. The coefficient is used in the equation to find the dynamic loss pressure for fitting. So, as an example, if the throat radius is 4.5, the spacing between the vanes is 3.25, the velocity is 2,000. So we want to find the row that has 4.5 and 3.25, okay, which is going to be the bottom one. We want to look for the row with the 2,000 feet per minute. That's the second to the right, or the column. The coefficient is 0.02 or 0.23. That's our loss coefficient. Okay, so the dynamic loss is coefficient times velocity pressure. So my coefficient is 0.23. My velocity pressure is 0.249. My dynamic loss is 0.23 times 0.249 for a 0.0573 inch water gauge or water column. Velocity pressure equals velocity divided by 4005. Okay, so if my velocity is 2,000, okay, my velocity pressure would be 2,000 divided by 4005 squared. So my velocity pressure is 0.249. Okay, you can calculate velocity pressure if the velocity is known. Okay, so again, VP 2150 divided by 4005, that's my velocity pressure of 0.288. Okay, we have another chart here. Okay, this slide shows the SMACNA loss coefficients for transition. Okay, this is also on handout 4. Okay, which I'll have on the online material. Okay. So a square road elbow with a turning vane has a feet per minute of 2,500 FPM. The vane throat radius is 4.5. The vane spacing is 3.25. Okay, so VP divided by V, okay, divided by 4005. 2,500 divided by 4005 squared Velocity pressure is 0.39. The dynamic loss equals coefficient times VP, which is velocity pressure. So the dynamic loss is 0.22 times 0.389 for a 0.086 water column. There's also loss coefficients for transition. Okay, and again, we have our A1 over A. Okay, the upstream area divided by the downstream area. Okay, so it basically tells us what our reduction is. A1 is my upstream. Okay, that's the closest to the air handler. A2 or A is the area leaving the fitting. Okay. And again, we use that. We figure out the reduction angle. Okay, 15 to 40, 50 to 60, 90, 120. Okay, what's the reduction angle? And we have our loss coefficients. Okay. This slide illustrates the included angle. Note the angle of one side of an equally tapering transition is half the included angle. An included angle of 30 degrees means that the slides slant in by 15 degrees. We do not normally lay out sides of transitions by degrees. Okay, the table in this slide shows common angles by pitch in 12 inches. This lets you estimate the approximate angle. Okay, so the included angle is based on the angle inside a 12-inch pitch. It's the slant of one side in 12 inches. So if I am slanting in 3.14 inches over the course of 12 inches, my angle is 15 degrees. If I'm slanting in 7 inches over a 12-inch period, my angle is 30 degrees. Okay, and if it's done on both sides, you have to add those together. Okay, so calculate the loss for this transition. What is A1? Okay, A1, okay, is 18 by 18, which is 324 square inches. What is A? A is the downstream size, 9 by 9. So A1 over A, so we take 324 divided by 81. A1 over A is 4. The included angle is over a 12-inch period. Okay.